population P of bacteria in an experiment can be modelled by the formula P equals 100 e to the 0.4 t, where t is the time in hours after the experiment began. Use the model to estimate the population of bacteria 7 hours after the experiment began. So t is 7. So if I substitute 7 into the formula, that's going to tell me the population P. So if I do 100 times e to the power 0.4 times 7, and I substitute that into my calculator, I'm going to get 1,644. That's the population of the bacteria after 7 hours. So that's part A of the question. Then part B, interpret the meaning of the constant 100 in the model. Well, the 100 is the initial population. That's the population when t is 0. If this bit here is 0, then I'll have e to the power 0, which will be 1, and so the population would be 100. So the number at the front there, 100, is the initial population. And then part C, how many whole hours after the experiment began does the population of bacteria first exceed 1 million? So I'm going to find when the time would equal, at what time the population would equal 1 million. So I'm going to take the model, make it equal to 1 million, and find when would this, what value of t would it equal 1 million? And then I can just say that t has to be bigger than that. So I've just made the population equal to 1 million, and then I've divided both sides by 100. I am now going to take logarithms of both sides. And now I can divide both sides by 0.4. So I found that when I type that into my calculator, ln 10,000 divided by 0.4, I find that I get 23.025 and so on. I need to say how many whole hours after the experiment began. Well, in terms of whole hours, I can see that 23 hours is not enough. 23 hours is just under 1 million. So it's going to have to be after 24 hours is when the population would be above 1 million. 23 hours, it's just below. 23.028 or 026, so on, it is equal to 1 million. So whole hours where it exceeds 1 million would be 24.